Okay, you may have seen this before because it's also in the notes, but I thought we'd do it as if we were in an exam. You've got an application here, an extended range prototype racing car uses a gas turbine engine to power a generator, which charges the batteries when they're depleted. The gas turbine has a single shaft, okay, connecting two compressors with a turbine, and those two compressors are known as a dual-stage compressor. Okay. And I've said for this example, we can see that KT1, which is this shaft here, has a spring stiffness of 2K, or torsional stiffness, and KT2 has half of the stiffness, K. And the moment of inertia of each of these compressors and turbines is equal to I. Okay, so they're all the same in terms of moment of inertia. And I've said, part 1, assuming no damping, write out the equation of motion in matrix form. And part 2 is calculate the natural frequencies of the motor states for the system. Okay, so this is, like I said, this is on Blackboard. And I shall... Okay. So, 2013 exam. Question 1. Essentially, we've got a 3 degree of freedom system. I could draw it schematically. I could draw it schematically like this, where this is I, this is I, this is I, this is 2K, and this is K. We've got theta 3, theta 2, and theta 1. So that's drawing it in the same way that you would have done with a mass spring system. Okay, here we've got torsional springs, okay, and we've got moments of inertia instead of masses, but it's exactly the same in terms of the method that you use. So the quick method, we've got our mass matrix or inertia matrix. It's basically the diagonals. We've got each of the masses or inertias. So we've got I, and I. And that's multiplied by the accelerations, angular accelerations. So theta 1, double dot, theta 2, double dot, and theta 3, double dot. We then use the quick method to fill up the stiffness matrix. Now if you remember, the diagonals were the springs connecting each mass to ground or to another mass. Well, in this case there's no ground, so we don't need to worry about that. For the first one we've got 2K. For this one in the middle, notice we've got a 2K and a K, so that's 3K for the one in the middle, and for the one at the end we've just got K, so that's just K there for the diagonals. But for the stiffness matrix, we can't disregard the off diagonals like we have done with the mass matrix. The off diagonals are minus the sum of the springs connecting each mass to another mass. Okay, so between mass 1 and mass 2, or inertia 1 and inertia 2, that's first row second column and second row first column, so these two slots here, minus the sum of the springs connecting it. So we've got minus 2K here and minus 2K there. The diagonals are the sum of the springs connecting each mass to another mass or to ground. Okay, you add them up. That's the sum. So for mass 1, we've got 2K, which goes in that box there. For mass 2, we've got 2K and 3K. We've got two springs connecting mass 2 to another mass. Okay, so 2K plus 3K is 2K plus K is 3K, so that goes in the middle. Okay, and for mass 3, we've just got K on its own, which is there. For the off diagonals, you take the springs connecting each mass to another mass, okay, and it's the minus the sum of those springs. So between mass 1 and mass 2, okay, which is going to be first row, second column, or second row, first column, okay, because the same spring connects mass 2 to mass 1, okay, minus the sum is minus 2k, there and there. There is no spring connecting mass 1 to mass 3, so we have 0 here and 0 here. Third column, first row, third column, and third row, first column, okay, 3 and 1. Can somebody tell me what goes in these slots here? Minus k, exactly. Minus the sum of the springs connecting 2 and 3. So k and minus k. And that's multiplied by the angular displacement. So there's the equation of motion. That would garner you 3 points. 1 point for the equation, and 1 point for the correct inertia and the correct stiffness. That's part I. Part 2, part A2, so this is question 1A. Part A2 says, calculate the natural frequencies and the mode shapes of the system. So you apply the substitution, in this case I shall apply the substitution theta, I, I'll call it big theta, cosine, omega t. That's I. So theta I double dot is minus omega squared theta I cosine omega t. So you plug them into your equation. So here's our mass matrix, I 0, 0, 0, I 0, 0, 0, I minus omega squared times by theta 1, theta 2 and theta 3 plus our stiffness matrix, so 2k minus 2k 0 minus 2k 3k minus k 0 minus k k. And the whole thing so you see where we've got theta double dot, we've replaced it with minus omega squared times by theta cosine omega t. Okay? Minus omega squared times by theta times by cosine omega t. And obviously where we've got theta 1, 2 and 3, for the stiffness we've just replaced it with big theta cosine omega t. That disappears, fortunately. You don't need to worry about it. Okay, divide both sides by cosine omega t and it just drops out. And notice we've got one matrix here times by minus omega squared times by thetas, and one matrix here multiplied by theta. So we can combine the two matrices together, and so I'll write it in the way that we want it. We've got 2k minus omega squared times by I, 2k minus omega squared times by I, then minus 2k and 0. We've got minus 2k here. We've got 3k minus omega squared times by I, minus k, 0, minus k, and then k minus omega squared times by I. That's multiplied by d to 1, d to 2, d to 3. Now, if you're familiar with that process, you can just jump straight to the mechanical impedance matrix if you want. You know, if you know the process of making the substitution and then rearranging the equations, you can jump straight from your equation of motion to the mechanical impedance matrix. You then have to define the determinant of this matrix. Okay, well, like I said, the equation for a 3 by 3 matrix is given on the formula sheet. It looks a little bit like this. Okay, there it is. And often, in this case in particular, there's no term in A31 and A13. Okay, and there's no term there. So often some of these terms will actually drop out. We don't need to worry about it. What I'm going to do is I'm just going to write the formula that I came up with instead of sitting going through it. So we have 2k minus I omega squared Nice. I shall leave you to go through the algebraic throws. Suffice to say that I ended up with this. Divide the whole lot by minus 1, which means that I end up with I squared omega 6 minus I squared omega 4 plus 6k squared I omega squared equals 0. And I notice that every term in here has an I omega squared. Here I've got an I omega squared, and here I've got an I omega squared. So I can take that out of the equation. This was omega cubed, actually. Apologies. Here. So I've automatically, this equation is only true if this equals 0 or this equals 0. Well, if I omega squared equals 0, then omega naught, okay, squared is 0. There's my first natural frequency. Okay, that's the zeroth mode. There's no natural frequency if the thing's not oscillating. But for the other one, I had to use the quadratic formula, and I end up with omega I squared, so 1 squared, is 3 plus root 3 k divided by I. which comes out to be 4.732 K divided by I. So again, the maths I'll leave you to go through yourself. So there's your natural frequencies, which it asks for. And the next part is the mode shapes, okay?
Have you got that natural frequency again, then?
How do I get the natural frequencies? Okay. I have an equation here, okay? This equation is only valid if this equals 0 or this equals 0. Now, if this equals 0, omega must be 0, which gives me this one. Okay? That leaves me with a quadratic. And if I apply the quadratic formula, okay, minus b plus or minus the square root of b squared minus 4ac over 2a, okay, I end up with two equations. Omega 1, I've said, is 3 plus root 3 k upon I. And omega 2 is 3 minus root 3 k upon I. Okay? And that's just from the quadratic formula. And again, you apply the numbers in there, or you apply these numbers and you get those two values times by k upon I. Okay? So those are the two natural frequencies. The first mode shape, or the zeroth mode shape, is easy. When the thing's not oscillating, everything will move in unison. Okay? You don't need to show the work for that. You don't need to stick 0 into your mechanical impedance matrix to solve for 1, 1, 1. Okay? I will take it that you know that. For the second mode shape, we need to take the mechanical impedance matrix. So I shall rewrite part of it here. 2k minus well, I'll rewrite it all here. Okay, so that's the general form in terms of the ith mode. Okay, and what you do is you take each of your natural frequencies and you plug it into your mechanical impedance matrix, solving for R2 and R3. Okay, this is R3I. And so for the mode 1, mode 1, omega 1 squared is 4.732 K upon I. So if I stick that into the equation, I get 2 minus 4.732 minus 2, 0, minus 2, 3 minus 4.732 minus 1, 0, minus 1, and 1 minus 4.732. So the first equation, I'll take the top line, we have minus 2.732 minus 2R2, 1. Well, if you actually work it out, they'll divide out, okay? Here we've got 4.732 k upon I. Well, that goes in there, the i's will cancel, and there'll be a k and a k, or you can just divide the whole equation by k and you end up with 1, okay? Or the various terms for that k. So minus 2.732 minus 2r21, obviously there's a 0 times this one, so we don't need to worry about it, equals 0. That means that r2, 1 is minus 1.366. Then we'll take the second line for the second equation, minus 2 minus 1.732 times by R2, 1 minus R3, 1 equals 0. You could have taken the second line, the third line, that would have given you, that will give you the same answer for this one. Okay, it doesn't really matter. That's because you've got 3 equations but only 2 unknown, so it doesn't really matter which one you use. Okay, and that means that therefore R3, 1, if you do the sums, comes out to be 0.366. So mode 2 so that's mode 1. Right, so with mode 2, we've got 1.268 k upon I. And so again, you plug that into your mechanical impedance matrix, which is what I've done down here. Okay, so up there it's the same thing, except for I've used mode 1. Here I'm used mode the second natural frequency. Okay, and again, 3 equations, but only 2 unknowns. I can go through solving for those values. So if I do the same process up here, we've got a 0. 1 minus 1.268 is 0.732 times by 1 minus 2 times by R2, 2 equals 0. R2, 2 comes out to be 0.366. I'm going to apply the middle equation. Minus 2, okay, plus 1.732 times by R2, 2 minus R2, 3 equals 0. r 2, 3 equals minus 1.366. So there we go. There's the second mode shape, or theta 2. Okay, so that, if you got all that right, that would have garnered you 17 points out of 25 for the question. Right, part B is given. Okay, so you can see part B, a spacecraft travels at constant velocity in deep space with the effective gravitational field of 0 carrying an instrument package with 16 kilogram mass supported by AV mounts of stiffness 500 newtons per meter. Rocket engine is suddenly switched on so that the craft accelerates at 0.2 g thereafter. Assuming zero damping, explain your reasoning, sketch the displacement x relative to the spacecraft of the instrument package as a function of time. Show the values for the extremes of displacement and period of oscillation on the graph. So it's not dissimilar from a question you've seen before. Essentially what we've got with B is we have a step forcing function. Yeah, you've got your we assume ground is the spacecraft, okay? There's a spring of stiffness K, a mass of M, and we have a force being applied, junk, junk, junk. F is going to be M times our acceleration, so that's going to be 0.2 mg. Okay. Other thing says, what's the sketch the oscillation? Well, we know for a step forcing function, x of t is f naught upon k, 1 minus cosine omega naught t. Okay, that's on your equation sheet. I haven't just popped up with that. It's there in front of you. Well, we can find out the various values. F naught is 0.2 mg, 0.2 times by 16 times by 9.81. We do the sums.
Space, so why are we using?
Sorry?
This is in space, so why are we using g?
Because the acceleration been given in the question, it says 0.2 g. Yeah. This comes out to be 31.392 newtons. And omega naught, which is the other thing we need to sort out, is root k upon m. And so the equation, obviously we plug these values into here, we get x of t The question asks for the sketch though. Now there's two ways you could approach to do the sketch. You could start and build it up. So first off you do cosine of 5.59t minus cosine is obviously the flipped over. 1 minus it shifts the whole thing up by 1, and then multiplying it by 0.2628 multiplies everything by 0.628. I shall just go straight for the solution. So ask for a function of time. Here's our x of t. Okay. Yep. So I'm just going to draw a dashed line here just to help me draw it out. And another one up here. This is 0. F naught upon k, so 0.0628. And this is 2 F naught upon k, so 1, 2, 5, 6. This is in meters, obviously. This is in seconds. And we're going to get an oscillation that's undamped. It goes something like this. This is 0. This is t naught. 2 t naught. And t naught is 2 pi. Okay. Okay. What would it look like if there was damping involved? It was slightly curved down, exactly. That oscillation would decrease in amplitude depending on the damping.